Okay. Again, so let me repeat what I just said. I thank the organizers for giving me the opportunity to give this course. It's a great honor to be able to present my work to probably younger people. So my course would probably be a bit of the main course of this, of the theme of this seminar or workshop, in the sense that it would be, I'll probably mostly work on the hypercubic lattice. So there'll be very few groups here, at least so far as this course will be concerned. But as we'll see, actually, many of these ideas actually have proven to be very useful to obtain results about Bernoulli percolation or more general graphs that Tom has been covering in his course. Okay, so I'll probably, whenever I get the chance, I'll hint on that. But yeah, but hopefully, it will provide you with some new toolkits that you can find application of in other areas. Okay, so the content of this course are mostly based on some of the recent works of mine with Ghosh from ICTS and University of Geneva, Pierre Rodriguez from Imperial College London, and Franco Severo from University of Geneva. Okay, so I know that Tom has already covered, has already given a comprehensive introduction to Bernoulli percolation. But the plan of my today's talk is to not jump head on onto the nitty-gritty details or all the techniques, but rather spend some time motivating the particular type of percolation problems I'll be talking about in this course, and the reason why it is important, not just in itself, in its own right, but also its relevance for studying problems in independent percolation, more classical model, okay? And for that, I think it's better to start with the fundamentals, okay? So if you are already bored, okay, hearing too much about Bernoulli percolation, so just hold with me for a while. But I think for those actually who are doing it new, I mean, we're newcomers in this fields, you'll find it probably not too off-putting. Okay, so let's recap. So here we are. And as I said in the beginning, I'll be working with the hypercubic lattice for the purpose of this course. So ZD, D is bigger than or equal to 2. And you already know why Z is not a very interesting graph for percolation. Okay, so the model, as you have seen from Tom's talk, is the so-called H percolation model, but you can also make sense of that for vertex percolation model. So what we have here, essentially, you have some kind of, you have a graph, let's say lattice, and some of the edges you declare to be open with some probability, P. So omega E, the state of the vertex at HE equals to 1, right, with probability P, and equals to 0 otherwise. So it's like 1 minus P 0. So these are the edges that don't stay in the graph that results from your experiment, and those are the edges that stay. And then these red edges, these open edges, that define subgraph, right? So you're starting with, more generally, you're starting with an infinite connected graph. That's your background. And you perform this experiment, this coin tossing experiment, if you might. And then you obtain a random subgraph, which is induced by these red edges, open edges. And you ask first, okay, essentially what you would like to ask is that it's large scale properties. So the first question to ask, the very qualitative question in a sense, is whether or not, so you started with an infinite connected graph. And the first question you ask is whether or not this graph consisting of these red edges, whether they have an infinite connected component, okay? So by the monotonicity of the model, as you know that, well, as P increases, as the density of the edges increases, the probability that you'll have a connected set increases as well. Although those of you who are already familiar with this thing, it's trivial, but those who are new, you can try to prove it rigorously. Why is that so? It seems so intuitive, but this will give you a good glimpse into some of the key tools in the theory itself. Okay. Again, I didn't attend Tom's first talk. I don't know, probably he already gave a proof of that. Whatever. So from the monotonicity of the model, you can easily see that, well, there exists some PC, right? There exists some PC, which is a priori can be in the closed interval 0, 1. Okay, there's nothing preventing it from happening that. And says that for P less than PC, you have no cluster with probability 1. No infinite connected cluster. Okay, so let me fix the terminology. When I say cluster, I mean a connected set, okay, a connected component. So there will be no infinite cluster. And again, it's connected in these open subgraph that you obtain by performing this experiment. So there is with probability 1 below PC, you have no infinite cluster, and above PC, with probability 1, there is an infinite cluster. Okay. Although there is a much subtle question whether you have, and you already saw actually from Tom's talk yesterday, that the uniqueness question is actually much more subtle for more non-amenable graphs. Anyways, for lattice at least, again, the proof is, you saw the proof of, I think Tom already gave you the Burton-King's argument that is used to prove the existence of unique class, the uniqueness of cluster in the supercritical regime for amenable graphs, in particular, the graphs I'm considering here, which is a hypercubic lattice. But, well, it's in general much more subtle question. Okay, but even before uniqueness, forget about uniqueness. First question to ask is whether or not this PC belongs to this set 0 or 1. Why? Because if this is a possibility, that it's very drab. It's not interesting, right? If this is 0, that means that you're always percolate, essentially. Of course, at 0 you cannot percolate because you have no edge, and at 1 you definitely percolate because you have the whole graph. But no non-trivial value of P, there's no non-trivial value of P at which you don't percolate. The other situation is also not interesting, which is that PC equals 1, that is, you never percolate. And for Bernoulli percolation, at least, and we'll see actually this order, this is a very interesting thing. The particular type of model I'll consider, we'll mostly spend time with throughout this 4 lectures. It would be kind of the order of difficulty of proving the same step would be reversed. Okay, we'll come to that. Let's hold on to the Bernoulli percolation for a while. So for one side of this, so where you would like to prove PC is bigger than 0, this turns out to be very easy. And as you have already seen, okay, let me repeat the argument, is essentially the fact that you can obtain a simple energy entropy argument, which is so ubiquitous in this kind of field. So you just say probability P is the probability measure corresponding to the density parameter small p, that there exists an open path, let's say of length n, starting at 0. Okay, so this is what? Well, this is, let me use, probably I could use my other notebook, but anyways, I think I can use that. Okay, sorry. Okay, so what is this? Well, there are 2 parts to that. First, what is the probability of a given part of length n being open? That's simple. That's just p times n, because they are all independent. And you will see this independence assumption is crucial in so many aspects here, at least for Bernoulli percolation. And then, well, we just multiply with number of paths of length n, starting at origin of length n, starting at 0. Okay, now what is that? Well, you know, we have you are in a, so this proof just doesn't only work for ZD. There is nothing, no ZD here. This just works for, you know, any D regular graph, let's say 2D regular graph. Okay, so you can take any Kelly graph with a finite number of generators. So, well, it's clearly seen to be 2D to the power n. So that's simple. Okay, so together that gives you 2D times p to the power n. Then you can easily see if p is less than 1 over 2d, then this goes to 0. But that cannot happen if you did have percolation, right? Because to have an infinite cluster, you'll have to have an infinite path, positive probability. Okay, so this says in particular that PC is bigger than or equal to 1 over 2d. Actually, let me tell you an interesting fact that PC for ZD is actually asymptotic to this value for hyperbolic. This is because of the fact that for tree, and also Tom talked about that, it is like looks like a Galton-Watson process, like a branching process. There it is exactly 1 over 2d. So this is the critical level branching process. Anyways, okay, so that part is easy. But other part, which is that PC is less than 1, is actually much more difficult. Actually, even for the hypercubic lattice, if you look and open this classical, the Bible, kind of like the, you know, you can say the Bible of percolation theory, where you first, you know, when you first entered the field, you entered through that. Is this book on percolation by GFF agreement. So in the first or the second chapter, I think you see the proof that PC is trivially less than 1 for Z2. Okay, and the argument is a bit more. So, for example, it needs a topological fact that, you know, you can. So for the supercritical, if you want to prove PC, that is for some P, you have percolation. You actually have to count, instead of paths, the number of ways it can be blocked. You can be shielded from infinity. Okay, and that is actually much. So it's essentially the counting the number of cut sets. Okay, or number, and which is for Z2 is okay because of the duality. It's quite easy that you just count the number of paths. But for higher dimension, you have to count surfaces, and that's not easy actually. Anyways, but well, once you know that, you know, you percolate in Z2, of course we percolate in higher dimensions because, you know, in ZD contains Z2. So if you percolate in Z2, in particular, you percolate in ZD. But let me just point out to you that for general graphs, this was a very big problem, and it was one of the main conjectures by Benjamini and Schramm in this 1996 paper, this famous paper, which just spawned so many works, and, you know, many of the conjectures that also Tom is talking about. And one of the things was that this very natural conjecture that if you have essentially some kind of notion of dimension, let's say some isoperimeter dimension is let's say, you know, bigger than 1, that's enough. That should be enough to tell you that PC is so some kind of isoperimetric dimension is bigger than 1 should be enough to tell you PC less than 1. And we essentially proved it for, at least for Kelly graphs in the recent paper in Duke. And it also, we actually were able to prove a much general result, also conjectured by Benjamini Schramm. But for that, actually, we didn't go all the way down to 2, but 4, anything bigger than 4. But anyways, we'll not talk about that. But anyways, but the take-home message from this part, this first slide, is that whenever you see a percolation problem, and we'll face a new percolation problem as we go along, of course, the first question you should ask is whether the phase transition is non-trivial. Okay, whatever that means. Good. Any question on this part? Okay. Right. But as I told you, this is just a course level picture. Okay. Of percolation. This just tells you whether or not percolation, you have a percolation for some parameter values and you don't have a percolation for other parameter values. Okay, so, but we would like to know more about it. For example, we would like to understand the local geometry of percolation clusters. What do I mean by that? Well, I would like to know, for example, in different phases, what are the distribution of the sizes of the clusters? How big are they? How do their intrinsic properties relate to that of the underlying ground, the background ground, that is ZD? So all these kind of questions are very important and extremely interesting. They give rise to very rich and very interesting research problems. But for that, PC is too coarse an information, just saying PC. We need a bit more careful characterization. So for that, there are two parameters, auxiliary critical parameters that are relevant. One, which I denoted here by PC tilde, and this notation, let me warn you, is by no means classical. So, you might see different thing. I just did it here for a different reason. So this demarcates the so-called strongly non-percolative regime. So what do I mean by that? So when P is less than PC tilde, it is not only that it doesn't percolate, it also means that the probability of connecting to a ball of radius L, okay? So essentially the event that you are, let's say, you're here and so let's say this is the event that I'm looking at. Sorry. Which is the radius is like L. So if this is the event I'm looking at, this probability, the probability of this is decaying like exponential in the radius. So what is the consequence? One of the immediate consequences is the following, that all the open clusters in this phase, okay, they have typically logarithmic, so if you look at a finite box, let's say look at a big box and of size n, and if you look at the size of the largest cluster, that will be typically of the size order of log n, logarithmic in n, okay? And if some of you are familiar with, let's say, arbitrary random graphs, that's kind of what happens there, right? When you have a subcritical level, you have logarithmic clusters as clusters of logarithmic diameter. Now, while it is, of course, okay. Now, it is not actually very difficult to see that. So, not difficult. That PC tilde is also less than 1. I'm sorry, that's of course not difficult at all because it's less than PC. What I mean is, of course, the other one, which is PC tilde is bigger than 0. Why? Well, just look at the proof that I just gave you. If you are careful, while I was telling it, you have noticed that this doesn't only give you that your connection probability. It doesn't only give you that, that you don't percolate. It actually gives you that you decay when P is less than 1/2D. You essentially decay like an exponential in little n, okay, which is the radius, okay? So that part is easy. So in fact, you also get that PC tilde is also bigger than 1/2D. But what you'd like to believe is that not only that, but PC tilde and PC are actually equal. Okay, that's the question, because that will be an interesting thing. That will tell you something all the way up to the critical region. So this is a question. This is a more difficult question. And I think, okay, so the first proof was for Bernoulli percolation was given by Menchikov in 1986, and a year later, a bit different proof by Azerman and Bursky. Now, in a more recent times, Hugo and François Tessiot gave a proof of this from very general graphs, actually. I think which also probably is the so-called famous 5PS argument community. I think Tom already talked about that also. Okay, any questions so far? Okay, now let's go to the supercritical analog of that. So this is what I call here as a strongly percolative regime. And here, what it turns out, the correct threshold, okay, to look at is the so-called slab percolation threshold. So what do I mean by that? So slab is essentially this, as you can see here. Okay, it's a thickening of Z2. Okay, so that's like a slab, infinite slab. And the slab percolation threshold demarcates the regime in which, so that if P is bigger than PC slab, then you actually percolate. In order to percolate, you don't need the entire lattice, but you can percolate in a thick enough slab. Okay. And again, so why this is important, as I told you, here I list some of the properties, some of the important properties of the infinite cluster that you can prove in this regime when P is bigger than PC slab. And this list is by no means exhaustive. The first is that, so for example, you can prove that in finite boxes, you'll have a ubiquitous macroscopic cluster. So there will be a cluster which spans everywhere and kind of like, permeates throughout the domain. Whereas the second largest cluster would be, at most logarithmic in size. Okay, so the picture will essentially be a big block. We'll see some picture later on, and with small kind of dust-like clusters. Then you can actually prove that what we call the chemical distance. So you see, the infinite cluster itself is an infinite connected graph, and it has an intrinsic distance, right? And this intrinsic distance, by the way, can be quite big, right? Because it's thinner, said. It can be quite big, actually, compared to the Euclidean distance, which is basically equivalent to the distance on the lattice. But if you have this assumption, and then basically, then you can prove that this distance is actually comparable, it's equivalent to Euclidean distance. Okay. Then then there is another one, which is, it's called the so-called truncated correlation function. So you see, like for the subcritical regime, we are looking at probability of connectivity that decays exponentially. For supercritical regime, of course, you cannot do that because, of course, you connect with the positive probability. The correct quantity to look at, the correct way to look at the rate of convergence is to require that 0 and x connect to each other through a finite cluster. Okay, and this is expected to decay. This is actually expected to behave like the near critical point. They are expected to behave. They are basically expected to behave similarly, but one being the analog of another in the respective regime. So this is also expected to behave decay exponentially. And this proof I can actually give you quickly. I think it doesn't take much longer. So here we go. Why actually it is true? So let's say P is bigger than PC slab. So what do you do? So let's say here is your 0. And here is your, so let me take a bit more space, I think. Actually, I can go to the other one. Let me use that one. Okay. So here is your 0. let's say here is your x. And what you do is that you cover up the entire distance, by slabs like that, where the length of each of these slabs is L, where L is chosen so that the probability, recall, because you see, I'm sorry, recall that we are in this regime that when P is bigger than PC slab, there will be a thickness for which I'll percolate through the slab of that thickness. Okay, so let's use that. Okay, so let L be such a width. Okay, so PP and 0 connected to infinity with Z2 times minus K dot K. Sorry, I'm using L. D minus 2. This is, by the way, this is actually, you see, this argument is only valid for dimension strictly bigger than 2. In dimension 2, you can actually use duality. The argument that tells you, you decay exponentially at P less than PC will tell you that you will decay exponentially, to find cluster P bigger than PC. Okay, so this is positive. So then what happens? Now, suppose there is a path that connects between 0 to x, but manages to avoid infinite, connecting to infinity through each of these layers. So what happens is that, you see, but we know, right? Because now everything is independent, right? Everything is independent. All these layers are independent. So you can argue carefully, but this is basically the idea is that in each of the layer, you are missing a positive probability. It costs you a positive probability not to connect to infinity. So, you're missing infinity at each of this slab, and you're paying a probability cost for that, just because of this. And assumption of independence is very crucial, as you can see in this argument. And so what you have then the probability would be, let's say, so this probability of, so if this is like, sorry, if this is like Q, then you pay a cost like this event will have a cost like 1 minus Q, because that's the cost you pay for not connecting in each of the slab to the number of layers, which will be mod of X divided by L. Okay, so that gives an exponential decay. Okay, so that's there. And you can actually prove plethora of other properties. You can prove that, for example, you can study the properties of harmony, the spectral properties of this infinite cluster, all using, where actually this kind of thing would be a very crucial input. Going to invariance principle, etc., etc. Now, again, this is not easy for here. Actually, this is again not difficult to see that PC slab is actually less than or equal to PC of Z2. Why? Well, because this definitely contains Z2, right? So if you percolate in Z2, definitely you percolate in a slab. And we know that is strictly less than 1. So PC slab is strictly less than 1. But again, just like in the subcritical case, it's much more difficult to prove it for that is actually same as PC. And in this case, it was proven by Grimmett and Mastro in 1990. And to the best of my knowledge, actually, all the cases, the only cases where actually similar results is known, for example, are basically some kind of, okay, this result for some other models, dependent models, but there is either essentially a modification of the given Mastro argument, except the case which is a close cousin of the Bernoulli percolation. It's called FK easing model. FK percolation, a model for Q equals 2. where actually it's known due to the work with you. Okay. So other than that, just before our work for this purpose, the model I'll describe soon, this is not known. I mean, you don't have it much. Okay. Good. So that's kind of the background. Now, in the next few slides, what we'll do is that we'll pose the same questions for a different class of models. Okay. So what is this new class of models? Okay, let me start with a model that I'm not going to talk about in this course, but there's a very related model, and this has a much more immediate appeal. Okay, arguably, because okay, so this is a model that is inspired by the problem of fragmentation of a domain, or of a cylinder by a random walk trajectory. It's initiated by Benjamini in the work in 2008. So this goes as follows. You look at the discrete cylinder, the discrete torus in the transient region in d bigger than or equal to 3. Okay, and what you do is that you run, you take, so this is transitive. So you take a random walk, you run a random walk trajectory from a uniformly chosen point in this torus. Now, this is well known that the time, if you allow the walk to run for a time like n to the power d log n, actually it is log of n square for d equals 2. So if you allow it to run over that amount of time, then the random walk, this is the cover time of the random walk, so order of that, of course. Then the random walk fills up the entire torus. Okay, there is no point that it remains to be hit by the random walk. However, instead of doing that, if you run the random walk up to a time that is proportional to the volume, which is
Subhajit, there's a question in the chat. There's a question in the chat.
Yes.
Can you see the chat, or should I?
Oh no, I cannot see. I just see.
Okay. All right. So the question is, when you say PC slab is equal to PC, do you mean PC of Z and not Z square?
Sorry, say that again.
When you say that PC slab is equal to PC, do you mean PC of ZD?
Oh yeah, sure. I know actually. Okay, so this is probably confusing. Yes, definitely. What I mean is PC of ZD indeed equals to.
Yeah, because it's not clear to me that, I mean, without I mean, just by knowing the definition, it's not clear to me that PC slab is not just equal to PCZ2. I mean,
no, that is yeah, sure. But it is not, as you can see now, because PC of ZD is strictly smaller than PCZ2. For D bigger than or D is strictly bigger than 2. Thanks.
Yeah. Okay.
Thanks. Thank you. Okay. Fine. But that's a very good question, and it's an important. You see, actually, that's why, I mean, that's a very wonderful aspect of it, right? Just a finite thickness is enough, to make you percolating. So even if you are not percolating in C2, you can percolate in a slab.
Yeah, it's surprising. Yeah.
Yeah, which is a thickening of that. That's a very, very interesting aspect of it. Thanks. Okay, so let me come back. Okay, so again, you run it until this time, and you have a picture, which is basically everything is filled up. Then what you do, instead, you run it until the time which is proportional to the volume. This is called the so-called Poissonian regime. And the reason is that when you basically run it until u times n to the power d amount of time, what happens is that if you look at the set of times, the occupied vertices, or let's look at the complement of that, which we call the vacant vertices, vacant set. I mean, the naming is clear because it's left vacant. It's not occupied by the random walk yet. This point, this has some kind of locally, you can, I'll soon just make it try to make it a bit more precise, not completely low, because I don't have time for that. But so they actually somehow are described by a Poisson point process. Okay. So in this regime, what happens is that a fraction of the volume of this torus that remains untouched by the random walk. Okay, that's the vacancy. Okay. Hence, you can ask very interesting percolation questions, and the questions are extremely natural to motivate. So what you want to know is that, you see, if you imagine random walks, and this is like in your mind, a thread-like object, right? And the question that you ask is that, you can imagine in dimension 3, you take a cylinder, like a piece of chalk, and you run it, run a random walk for long enough time, whether at some point of time, the chalk will fall apart because, as the random, so you can imagine the random walk is traversing, so the random walk trajectory is being followed by some kind of like, some kind of fluid, which is basically erodes the chalk as it goes through, and it completely, as it goes, so it completely remove the particles there, and ultimately it breaks apart. So the disconnection problem at random walk is a very natural problem. And the question you asked, so now actually gives rise to a very interesting percolation problem. Now, at this point, since you will actually follow both of the, okay, there are 2 more talks by Tom, and there will be 4 more, you have to be with 3 more by me. I'll be using a different convention compared to Tom, and for a reason. So, but I hope that will not cause much confusion. So let me spell it out here. As we have guessed by now, this parameter, so this parameter U is will be this kind of density parameter, or in this context, it is known as intensity parameter, which is the analogous parameter, the parameter which is analogous to P, the density for Bernoulli percolation. But note this, that unlike in the Bernoulli percolation, and it's just clear, I'm sorry, that as U increases, the vacant set, the vacant set decreases, right? Because as U increases, you have more and more trajectory. The super trajectory occupies more and more space, so the vacant set gets thinner and thinner. Okay, so the conventions will be opposite. Okay, so small u means supercritical, big U means subcritical. Whenever you feel confusion, just interrupt me and I'll clear it. It's difficult to actually carry 2 conventions in mind, I agree, but you'll see probably why this is much more natural for this context, but yeah. Okay. So here's a simulation. And again, it's credited to David Windisch. So where we see the picture corresponding to n equals 200. The red cluster, this red thing here, indicates the largest connected component in the torus, whereas the blue, the second largest component. Now, those of you who are wondering, how come there'd be only 2? I mean, I can see 1, 2, 3, 4, 5, 6 maybe, but there are also 1, 2, 3, no matter how known. Just remind yourself that we are looking at torus. So these 2 faces are glued together, so are these 2 and these 2. Okay, so so this blue cluster are indeed connected, not in the lattice but in the torus. Okay, fine. So okay, so what is the picture that we are seeing here? Okay, there's a simulation corresponding to 3 values of U. You probably cannot see that, but it doesn't matter. But the leftmost one corresponds to a value of U which is the lowest, the smallest among the 3, and this one corresponds to a value which corresponds to the largest among the 3. And what you see here is something. Let's look at this one and this one. You see this picture, in this picture, something akin to what I called earlier as a strongly non-percolative regime. You see that all the clusters, blue or red, it doesn't matter, it is the largest, and the largest one are quite small. They're quite sparse and small. Okay. Whereas in the leftmost one, which corresponds to the value of U which is smallest, again, recall that the convention is opposite here. So this should be something like a supercritical or more supercritical. Here you see a picture which is akin to the picture I described for you as under this title of strongly percolative regime. So you're seeing a ubiquitous red cluster, which is ubiquitous. It's like kind of like everywhere. It permeates throughout the entire torus. And there is a tiny little, the second one is so small. Okay. So this is a picture, that is familiar, should sound familiar to us. And this is something more like you see, we are getting a more balanced, kind of like intermediate phase between these two, where we are approaching criticality. And you see the red cluster is getting smaller and the blue cluster are getting bigger. So that ultimately they both. Yeah. Okay. So this is more like a, think of like a critical picture. Anyways, so yeah. Okay. So to understand, now the thing is that this percolation process is defined in finite volume. Okay. And it's actually so let me just see if I tell it here. Okay, so okay, I think this is a good place to tell it. So what Benjamini and Sidman, this is before random. Okay, what I'm going to say next. What they proved is that they proved, if I'm not mistaken, I think they proved this picture. Okay, they proved some form of this picture for high enough dimensions and small enough u. Okay, so you. For all u small and d large. Okay. But of course, the understanding of complete picture remained open. And then came this now seminal paper, the Annals of Math paper by Snitman. It was in put in archive. It started this thing I think 2008. It was published in 2010, where to address this kind of problems, he introduced a model in the infinite volume, okay, which he called random interlacements, which he describes in large n limit this picture of the picture of this random walk trajectories that you can see here. I'll not describe random interlacements in this course. I'll not give a precise definition, but let me just say that it's essentially what it is that it's a Poissonian ensemble of bi-infinite random walk trajectories, okay, which is ordered by basically this intensity parameter u. Okay, so the more the u, the more trajectories you see, and so the analog of vacant set for this disconnection problem is the vacant set of random interlacement. Okay, what is the advantage of that? Well, now actually you have a very stationary and okay, it was also stationary earlier, but anyways, you have a problem. You have like our familiar set of a percolation on an infinite volume. Okay. So you can start doing things, trying to obtain your regular properties that you prove for Bernoulli percolation. So then actually what you give rise to, there are actually two types of works. Of course, more and more understanding started to be obtained with several works, beautiful works like, there are many replications from the random interlacement side. In parallel, people started getting better and better coupling results. What do I mean? So coupling means, well, as I told you, you can actually, so this is, okay, I think I have already here. So this describes the local limit. So that's a statement, but you can make it more quantitative. You can actually actually in the same probability space, define this model and as well as this model so that, they are the occupied sets described by them are very close to each other in some metric. Excuse me. And you can get very good quantitative bounds on that. And this became better and better by a series of works that I mentioned here, I think culminating in this one, Sonny and Teixeira in 2016. So what happened is that this actually enabled one to create a dictionary where the result obtained from this vacant set, this population, could be translated to answer similar questions for the disconnection problem, the torus, okay, which has a much more natural appeal. Now, well, apart from again, and this somehow actually to understand that there are several. So let me tell you one actually beautiful property of this. Okay, if you don't look at the vacant set, I mean, why actually, you see, I'll come to actually a more probably down to earth importance of this model, starting this model. But before that, let's look at some fun parts and fun trivia. So instead of, so this enjoys a very deep connection with properties of random walks and as such. So for example, if you don't look at the vacant set, you can ask me, why look at the vacant set? Why don't just look at the occupied set instead? Well, the first thing is, you see, as I told you, if you look at the vacant set, so the definition of the random interlacement, you have by infinite random walk trajectories, okay, in transient domains. So they are, by virtue of being paths, they are connected. So you have infinite connected sets. So that question doesn't make much sense, okay, no matter what the intensity. Okay, so that's why actually you don't do percolation with that. But you can ask the next big question, uniqueness, okay? I mean, you have this super cluster. So let's say, I don't know. So here, some kind of by infinite paths coming here, there, thread-like objects, maybe. They're all infinite. So they all from infinite connected sets. But do they clump together? Whether there can be more than one cluster? That's a very natural question. And the fact is, they form an unique cluster, no matter how small the intensity is. For all U positive, you have a unique cluster, okay? And and here actually you see this Botvinkin's argument. If not, you have to come up with some kind of more sophisticated versions of that, because you don't have this so-called insertion tolerance and such. I'll come to that soon. So this is a very interesting fact. And there are so many beautiful things that you can say about this. Okay, now coming back to the vacant set. Why this is important? The first thing is this fact. So what I write here, it is the covariance between the states of two faraway points. So where the 2 points x and y are both in the vacant set. Now for Bernoulli percolation, even for those x parts, if you don't know, okay, maybe for random cluster models, for those who don't know random cluster models, don't bother. At least conjecturally, at least for FKZ model, at least of critical phase, this covariance decays exponentially. But and of critical phase, at least, you have a decay of truncated, exponential decay of truncated correlation. But here you are seeing something very interesting. Throughout the phase, no matter what the value of throughout the parameter range, the decay, like what is saying, is the Newtonian potential, okay, in the distance. Why? I mean, this actually is not difficult. You can actually, essentially, this is related to the fact that, if you take a random walk, the probability that transient regime that you will visit y is like the Green's function. It's actually proportional to sorry, I misread. It's proportional to the GZD, the Green's function, and that is like 2 minus t, as you know. Okay, so it's a polar decay. It's not just any decay, but what is very more important here is particularly slow decay. What do I mean? So one consequence of that is that if you, let's do a simple calculation. Let's just sum it up, okay? Let's just look at, I think let's not solve much. Let's say sum of the covariance. Let's fix 1 point. So let's say 0 belongs to view, and x belongs to the vacant set. And let's sum it over all ZD. Okay, so that's just sum. Sorry. Sorry, I'm not very good at this yet, as you can see. Yes, using this. So you do the sum of mod of x minus 2 minus d. You just split it in surfaces of radius n. So I think I should write much more appropriately. It's not really equal to, of course. I make your favorite meaning of that. So that is n to the power 2 minus d times n to the power d minus 1. Right? That's the length of the surface of radius n, and multiply with Green's function. This diverges. Okay. What this means qualitatively? It means the following: that if you condition on one vertex to be open, it throws open on an average, in expectation, an additional infinitely many vertices. Okay, so its range of dependence is kind of like, so this like is an infinite range, truly infinite range of dependence that you have, that you have to deal with. And that's something makes it such a very interesting ground for developing robust techniques for answering classical questions in percolation theory. And so it's very, very important because there are very natural percolation problems that now that's coming from, you know, studies of series of random functions and of different sorts in different spaces where you have these things come very naturally. Sometimes this kind of correlations are enforced by the, you know, regularity of the space, you know, the functions that are there. So it's very important to develop techniques for that. Okay, so you have that. So, and the second important thing is that, which is also related to what we just said, unlike Bernoulli percolation, and I hope actually, I think he has also mentioned about, Tom is mentioning about what is called the finite energy or insertion tolerance, terms like that. So what all of them imply is some kind of flexibility. Okay, so you can, so the models are amenable to local modification. You can locally modify the configurations, and that is very helpful actually. That allows you to perform local surgeries. Okay, and you can jump from one event to another. You can show that certain event exists from the existence of much more convenient event and do things like that. That doesn't occur here. You don't have the luxury always here, at least unconditionally. And let me give you the very extreme example to convince you why that is not, and that is actually because that's very easy to convince you about, is the following picture. So let's say your point, or a point on the origin. Okay, that so let's say I don't know the state of the origin, but what I do know, I know points around. Okay, so here are points around in my graph. And I know that they're all vacant. Okay, so let's say they are all vacant. So this, let's say this for vacant. But what does that immediately tell you? All the neighboring vertices are vacant. That immediately tells you, that forces you to declare this to be open. Why? Well, remember, how does a vertex given become closed in the percolation model? That is, it gets occupied, right, by the random walk trajectory. You have already declared your neighboring vertices to be open. So you see, and it is a bi-infinite trajectory that is coming for you, right? It's a bi-infinite trajectory that's coming. So in order to occupy in order for you to be occupied by a trajectory, it has to enter through the neighboring vertices somewhere. But they are vacant. Okay, so it just basically forces the random walk trajectories to go around it. So you immediately know the state of the vertex. Okay, this just, I mean, there are more subtle things. I mean, you can probably cook up, okay, what about that, but you can see actually you will not have this uniform properties. And that actually makes it much more interesting and difficult to deal with in practice. Okay, any questions so far? Okay, if not, let's go to the model that we'll actually spend time with in this course, which is a relative model and has very interesting properties. and arguably, in a certain sense, more tractable. This is the so-called Gaussian free-field level sets. So what is it? Again, it's something related to random walks. So you start with a lazy simple random walk on ZD. Okay, so we'll denote by Px's law. And its Green's function is essentially, I already talked about that, but let me define it for the sake of completeness. Is essentially for the simple random walk, it's so gxy is the expected number of times the random walk starting from x visits y. So the laziness has been okay. So now this defines a kernel, okay, on ZD, and it's actually a non-negative kernel. Actually, for that, well, you can show that. You can actually square root this thing by. That's actually I said lazy. So you can break it up the random walk into midpoints of the lattice to show that this is square rootable. So now, if I have a non-negative kernel, you can define a Gaussian field with that, right? All you need to define a Gaussian process is an assignment of means, which I take to be center. That is all the variables have mean 0, and I set their covariance kernel to be the green kernel on the second. Okay, that's that. So in particular, they decay like this. They exhibit this parallel decay that we saw for random intervals. Okay, how do you define? So how do you define percolation model? How do you create a percolation model out of a field? That's very easy, and you will see why actually this direction of this reverse direction of monotonicity becomes natural kind of. Well, what you do? Well, it didn't have to be probability, anyways, but you just look at its level sets. Okay, so you just look at the set of points where it's above a certain height h. So what you do essentially, if you're looking at some kind of, let's say, landscape of the field, sorry, I will use that. If you some kind of landscape of the field, what you do is that you cut through by a plane, by a horizontal plane, and just look at the points where you have peaks above the plane. And those are the points that define a random subset of your lattice or the underlying graph. And that's your side percolation process. And as I told, again, the direction of monotonicity is reversed, right? Because as h increases, as you increase the height, the number of points, the set of points where the field value is larger than h becomes smaller and smaller. Okay, and the question is then, connectivity properties of this level set as h varies. And from this property, you can actually, again, similarly derive, convince yourself that the covariance of indicator, which is essentially whether or not the vertex is open, and it also decays like Green's function. Okay, good. So nice. And you similarly define again the direction is opposite. That's why you have infimum instead of supremum. The A star D is just basically the critical height. So above which, if you increase the height further, you will have no connection. Okay, with probability 1, and below which you will have a connection. You will have an infinite cluster. Okay. Now, right. So now let's apply this. The guideline that I set out and that I laid out at the beginning of the talk is that whenever you see a new percolation model, first question to ask is whether or not you have a non-trivial phase transition. It turns out, in this case, okay, so what does it mean here is that, well, in this case, since it's just reparameterization, whether H star does not belong to minus infinity plus infinity. Also remember, I told you that, and probably remember by now, for Bernoulli percolation, the situation is quite different. For Bernoulli percolation, we remember that PC is, for the PC is bigger than or equal to 1/2D. That part was easy, right? The existence of a non-trivial subcritical regime was easy, whereas the supercritical regime is in general difficult. Here, and this is very important, and I'll tell you in a moment why, is kind of opposite. Okay, so let's look. I think it's fun actually to see why. Okay, why it's easier to prove in this case that H star. So remember, the direction is reverse. So if I want, so what I'm going to say is that it's easier to prove that you have a non-trivial supercritical regime. And how do I show that? So what does it mean in terms of A star is that A star is bigger than minus infinity, right? Because it's, you say again, remember, it's opposite. So in to Bernoulli percolation, that's the easier way to recognize. For Bernoulli percolation, the supercritical, non-trivial supercritical regime would correspond to PC is strictly less than 1. Here it's opposite convention, so that's why I'm saying that A star is strictly bigger than minus infinity. In fact, let me try to prove to you, okay, not I'll prove, but like a handovering proof, that A star is bigger than or equal to 0. It's actually non-negative. How it goes? So what do you do is that let's look at origin. Suppose, so there is an event, right? So let's say, let's say E, that that 0 is not connected to, so let me erase it. Sorry, let me write it here. So let me define E to the event that 0 is not connected to a big box. Okay, let's say box of radius n. We'll send n to infinity at the end. Okay, in bigger than or equal to, so there is a parameter epsilon x minus epsilon. Okay, epsilon is bigger than 0. Okay, I'll show that this event, this probability is goes to 0. Why so? Okay, now let's look at the event E. This event. Suppose what happens in this event, that when you don't connect, what happens is that, so if you, let's say, if you draw a big box, as in, again, it's not too bad, like better than I thought I'd be able to draw. So right, and so this is the radius is the radius is n. Okay. Okay. Now suppose E happens. This event happens. So what will happen then is that if you explode the cluster, of the boundary in this set, you'll hit a roadblock. You'll not be able to reach the origin. So what you'll have, reach an interface exploding from outside. Okay. Such that in the X boundary of that, what does it mean in this? Imagine this is like a, the set. It's like a contour. Here, throughout, you will have less than minus epsilon, right? Because if you didn't hit any such layer, then you would be able to go all the way in and you will essentially connect to 0. But what's the impact of that? And there actually comes in the very interesting property of Gaussian free field, which is that makes it so important in other branches. In probability, is one of the favorite objects of probabilists is a Markov property, the domain Markov property, to be exact. So what it says is that, well, you can actually realize this set by exploding from outside, from the boundary. Okay, so you didn't do anything, you didn't reveal anything inside. Then now you condition on that. Okay, when you condition on that, what will happen inside? If you look at the field inside, this is also a Gaussian free field on this domain. remember like a one-dimensional Markov checks, okay? So kind of like future given present is independent of the past. So present is kind of a blocking layer between future and the present, right? So something like that here. So the graphical version is that this is a layer that blocks the outer and the inner. When you condition on the outer, what all matters is basically the boundary part. And so what you get inside is again a Gaussian free field. But now, so let's call this domain, sorry, D. So what we'll have is that is a random domain, conditionally on whatever you have observed. It will follow again a GFF on this domain, but with a mean, which will be like the harmonic average of the boundary in the interior. Okay, so if you take any point, so one way to describe it, you know, many ways. If you take any point here, and if you send out a random walk, okay, and wait until it hits the one on the boundary. Okay, so this induces a probability measure on the boundary, and you take the average. So you take the average value of the field with just that probability measure. So this is also like Poissonian Regime, if you know. So that's your mean. So what happens here is that if you, so now what we know, along this boundary, you're always less than minus epsilon. So in particular, if you look at the value of the field at the central point, it has a mean which is at most minus epsilon, right? Because, you know, the monotonicity of expectation, everything is, you are taking an average of everything that is less than minus epsilon. So their average value is less than minus epsilon. So now under this, what happens is that conditionally phi of 0, conditionally on this expression, so this will follow a Gaussian, a normal random variable, okay, with mean which is less than or equal to minus epsilon, and some finite variance, some constant order variance. Okay, let's say, okay. But the point is that what happens then? So then what it means that probability that phi 0, sorry, because, you know, you have a, you know, like a Gaussian distribution symmetric around its mean, right? So I immediately get, given this data, so let's say given this event that I defined is actually half. Actually, it's more than that. It's actually bigger than or equal to half, because the mean can be more, right? But this is something not quite doesn't match up with what phi 0 is, because you see what phi 0 is. Phi 0 is a Gaussian variable, unconditionally is a Gaussian variable with a mean 0 with some variance. So the probability, the same probability that is bigger than, less than or equal to minus epsilon, it's strictly, okay, unconditionally, it's you know, it's strictly less than half. Now you can convince yourself that these two can only happen if the event, you can describe this discrepancy only if, you know, so only if this event E epsilon, the probability of that event is smaller than something. It's smaller than, strictly smaller than 1, okay? Which basically tells you that you have a positive probability of percolation. So you say, if you didn't have any percolation, then the probabilities of these events will go to 1, okay? You can imagine. So imagine like that. If this is like, if this were event of probability 1, this would basically say that, okay, the conditional expectation is exactly the same as unconditional expectation, but that gives you a contradiction. Now, why this is important? Similar idea. So the fact that the observation that the Gaussian free field, for free field, you can prove this part quite easily, was actually quite instrumental in the proof where Hugo, Franco, and Ariel and Aran proved that you know, in general graphs, you have a non-trivial under certain conditions in the isopyramic dimension. There is a non-trivial phase where you percolate. Okay, we actually defined it Gaussian free field first. We proved it for that, and then we deformed that into a Bernoulli percolation model. Again, the phrasing that I just used would be more, I think, would be more clear as you go along the course. Anyways, but that's just aside. So this part is easy, that A star is strictly bigger than minus infinity. However, interestingly, the other part is much more difficult. A star is strictly less than infinity, which was kind of, as I cannot emphasize enough, which is kind of opposite, which is trivial for Bernoulli. So it was proved that first in dimension 3 in paper 1987 by Brigmont, Leibowitz, and Mies, but their proof is not robust. It uses a very particular property in dimension 3, which is that essentially that a line, an infinite line, is a recurrent set for the random walk in dimension 3, but it's not for higher dimensions. It's not robust. And then what the story goes, that I think it's probably relevant since when we're talking in India. There was a birthday conference of Bharadhan, and then Leibowitz posed this challenge that proved this thing for all dimensions, and Stillman was present. And a few years ago, he already published did a similar problem for random interlacement. Then he and my colleague Rodriguez was a student, quizzed a student, they solved this problem together. So what they did, they proved something stronger. Okay, so here they defined, and they instead proved that the finiteness of an auxiliary parameter, which they call A star star t, and which is defined as follows. If your height is above this threshold, your connection probability, okay, of annuli, okay, with the commensurate radius, so let's say BL and B2L, okay, they are positive along some subsequence. Sorry, I'm sorry. So if you're above H, you are strictly bigger than A star star, then yes, so along a certain subsequence, this annuli crossing probability, they go to 0. Okay, we'll come to the reason behind this and the advantage of this weird definition later. But using that, what they proved is that, well, they proved that this threshold is finite. First, it is clear, it should be clear that this threshold is strictly bigger than, it's not less than, cannot be less than A star. Why? Well, you see, if you're above A star, okay, then you don't percolate. In particular, this probabilities go to 0. So you're definitely above A star star. Okay, so there is a one side. So it's bigger than A star, and they proved the finiteness of A star by proving that A star star D is finite. Now, why is the title of this slide called Strongly Non-Percolative Regime? Well, it's because of the following reason. They also proved the following, that if you are above, strictly above A star star, then not only you, of course, something like this happen, that your annuli crossing probability go to 0 along some pseudo virtues and subsequence. In fact, the connection probability, they decay straight exponentially fast. Okay, so this is like a weaker version of the strongly percolative regime, non-percolative regime we're talking about. So it means that, well, maybe not logarithmic, but the biggest clusters in a finite box, biggest open clusters, would be polylogarithmic in size. These exponents were understood much better in subsequent works. For example, it is known that it's actually exponential decay in dimension 4 and higher. Finally, in dimension 3, it's more nuanced. And we're in the last of these lectures, 4 lectures, I'll talk about a very recent result, where we're actually surprisingly able to obtain the precise large division rate, of this connectivity function, which is not very common in non-planar case even for more classical models. Anyways, okay, so they prove that you have at least a non-trivial, strongly non-percolative regime. And there is another work. Now, not much was known then. Well, like that, you'd expect that A star star D would be equal to A star. Before our work, the closest that did exist was something like this. And you should compare this to this trivia that I said in the beginning of the talk, that, the percolation threshold PC of ZD, that's asymptotic to 1 over 2D. It's related to that kind of, in a sense, that they showed that Drewitz and Rodriguez, that both of them are asymptotic to square root of 2 log D. Okay, so they're asymptotic to same value. Okay, so this is a picture we are now, possible picture. So we have an A star. We know that it exists, and there is an A star star, which is possibly strictly bigger, maybe, maybe not. At least we'd like to prove that it's not. And to the right-hand side of A star star, you have a rapid decay of connectivities. Any questions so far about meanings or results? Okay. So let's now come to the strongly percolative regime, okay, which is the other analog. Here, and when I was presenting to you the argument, this slab percolation argument for showing that we are this truncated 2-point function, the probability that 2 points are connected in a finite cluster decay exponentially fast. You might remember that so independence was a very important part here, right? In this thing, independence is very crucial to say that when you export this part, the fact that you're connected to infinity is not affected by the information at all. But that's not the case at all. It has a strong dependence. This quantity itself is not the correct quantity to prove that. Okay. So here, this is a mouthful, but let me try to describe to you. Okay. Let me take a bit of time. It will be familiar, very familiar to those who are, those who are used to this, but let me take a bit of time. So what is important here is some kind of event called the local uniqueness. So this consists of 2 parts. One is existence. So it says that if you look at the level sets confined to a box of scale L, which is a parameter of the event, you have a macroscopic cluster. Okay, means with the size, the diameter proportional to the size of the box. Okay, that's the existence part, that you have a bigger box. The next property is called the uniqueness part, which you can think of again, as I told you, this picture, strongly percolative picture, where we say that for all clusters C1 and C2, okay, which are big enough, and it's useful to define the notion of big hair in this part to be a slightly smaller than L over 5. We'll see, try to see why. Anyways, so let's say L over 10. Again, 5, 10 doesn't matter. But you'll see the order of the constants, the way they're defined, do matter. Okay. What it says is that, well, as long as you have 2 big clusters in this box, in the level set confined to a finite box, you can actually connect them in a twice bigger box. Now, what is the usefulness of this kind of definitions? So let me tell you what. So let me draw a picture. Okay. So let's say, okay, so let's see. I think we'll end up with this thing. And then actually, much more time than that. Okay. So let's say, draw a box. Okay, now I'm afraid whether I'll mess up this part, but whatever I draw, assume that to be a box. Okay, it's not quite, but it will work. So there are 2 side by side. Okay, what I'll do actually, I'll use these 2 events. So let me again go back to this. I'll use these 2 events. Sorry, I'll use this uniqueness and existence in adjacent boxes to glue them, to glue these 2 clusters to make bigger and bigger clusters. And using that, we'll be able to show, for example, events like, you have an infinite cluster, or, a big set is connected to infinity with a very big probability. The things are kind of things that you usually use the slab percolation kind of, argument to conclude in a Bernoulli percolation case. Okay, so let's go there. Okay. So let's say you have, sorry, so you see, I still need to learn. So let's say this is a side-by-side box I placed midway, okay? And what I mean is, so let's get some idea of the scale, I think, okay. So what do we have here now? Two L boxes placed side by side, okay, with the half overlapping. And let's say in both of these cases, I have both of these events. So I have local unique HL for the left one, intersected with local uniqueness HL also, but now for the translated version. So this means basically I'm translating the event. So the same event for this box, okay, for this box. Okay. Now, so if both of this even happen, first thing, from the existence part, I can get two macroscopic cosines, let's say something like that. Okay, so they are both bigger than or equal to L over 5. Remember, this is 2L over 10. Why this is important? Probably you can already guess, but we'll come to that later. But let's say, okay. So you have this two, and so then what I can do is I draw a twice bigger box around that. So around the midpoint. So let's say assume this to be a twice bigger box, but although it is not, but assume that. Okay, so let's say, so this part is, let's say, sorry, what I want to do is just draw a straight line to L. Okay, this is the length. Now, right. And I would also like to, right, I think I also need, so let me also include another event. I would also include to that yeah, I think that's useful. Yeah, okay, let's do that. Probably you can do it without it. Okay, so what I'll also assume on top of that is that local uniqueness on H2L, okay, on this bigger box. But then what happens? You already have two by the local uniqueness at smaller scale. You have two macroscopic clusters of length L over 5. Okay, each one of which is as length 12 over 10 with respect to the length of the bigger box. But since we have a local uniqueness at scale 12, so remember, so I have that they are connected, right? The two are connected. So what happens is that, you know, even bigger box probably don't have a space, but you know, but let me just use thing that even a bigger box, these two things, not too big, become connected. Okay, now what is the usefulness of that? Well, see that if the following is true, that for all L bigger than or equal to 1, I have this stretch exponential decay on the probability that you don't have local uniqueness, then this event is actually, you know, these probabilities are highly summable. Okay, so what we can do, you can build these gadgets. You can build these gadgets like that, you know, in successively higher. You just do the same trick, you know. Again, you push, you record the same thing at this scale 2L and do a bigger box. And as you go up the scales, this bound is getting better and better. So just by playing union bound, okay, you just sum up, you'll see that with the probability, if you're very close to 1, you'll have an infinite cluster. Why? Well, because you're connecting every cluster using exploiting the existence and uniqueness recursively to build bigger and bigger clusters. So that's why they're so important. And later, actually, I'll also talk about, spend a good deal of time about renormalization. And here, actually, you see, this kind of things are very important. So what does, so let me finish with that, I think maybe, is that what does renormalization do is that, you know, in order to solve the problem, you convert it to a problem in a coarse-grained lattice, okay? And you convert your percolation problem, the problems that you, let's say some kind of realization of some kind of geometric structures, one of the problem is to convert it to an equivalent problem for a coarse-grained lattice. Okay, so that solving the problem for coarse-grained lattice will actually give you a solution for your original lattice or graph. Here you can already see that happening, right? So here, what does it mean? So you can define a percolation process on these boxes, right? I'm not talking about going up the scales. Let's say in a fixed scale, okay, where two boxes are, they are open if you see the local uniqueness, okay. So then what happens is that in this percolation process, which is basically kind of a coarse-grained percolation process, because here the state of being open or closed applied to boxes instead of points. If in nearby boxes you have these events, if you have two open boxes side by side, or if you have a path, right? If you have this kind of like this chain of boxes, let's say, if you have a chain of boxes side by side going like that, what this enables you is that this event, if you have this event, like, so if you have a percolation of open boxes, in this process, but this local uniqueness event, the definition enables you to say, well, I also have a big connected component, right, in the original graph. And that's very crucial as something, and finding out this events cleverly is very important. Okay, so let me finish with this definition and then I'll move on. So I think probably I'll take 1 minute to say the plan of the next 2 lectures. But okay, as I told you, so we define similarly a level H bar says that for all, says that, whenever you are below H bar, okay, your local uniqueness events at all scales satisfy this bound that you see here. But the argument I just presented to you, it should be obvious to you. If not, interrupt me, I have not done my job well, that H bar is less than or equal to H star. Why? Because if H is less than H bar, that is, you have this property, then you are able, by this performing these tricks, to build big infinite cluster with the probability, strictly positive probability. Okay, so right. In fact, that's a nice exercise actually. When you're about to leave, is that doesn't only imply existence. Okay, I gave you the proof of that, but it also gives you the proof that you have a unique cluster. Okay, so here the proof of uniqueness actually, so you see, if you later on manage to prove that H bar equals to H star, we actually managed to prove the uniqueness. And proving the uniqueness for H below H bar is, I claim, is easy. Okay, if you have understood the argument that I just presented to you. Okay, you can try that. Let me just finish with a bit. So the plan that I just want to say to you in the next 2 lectures, but I'll finish a bit more. So the next lecture, this is a rough plan, but there can be overlaps. I plan to talk about this okay, so I didn't talk about that, but for the moment being, I'll talk about H tilde, but for the moment being, think of it as H bar. Okay, we don't know whether these two values are equal to H star or not. And for my next day's talk, my focus would be to prove that these two values are equal. And as you already know, that H star is sandwiched between these two, because I just argued to that. This will imply that you have these properties, nice properties of Bernoulli percolation at all the points other than the critical point. Okay. And then in the next one, I'll actually talk about this thing called like beyond H bar and H star. So for example, I told you that H bigger than H star, you have an exponential decay, a stretch exponential decay, and below H tilde, you have some other nice properties. Probably I didn't get much time to talk about that, but we'll prove that, okay, how actually in this regime, these are the regimes where actually you apply this renormalization arguments that I hinted at, and I'll actually discuss one of that in detail. In the last lecture, we'll say that how actually you can push this renormalization techniques a bit more and can take advantage of the connection the rich interplay this model enjoys with the potential theory for random walks to explicitly pin down up to a principal exponential order, the probability of connecting 2 points through a finite cluster, at all the points other than the criticality. That's very interesting because you usually not able to do that even for more classical models in non-planar case. And Tom also talked about that in a bit, like he underlined the difficulties. Okay, so I think I'll stop here. I took much of your time, sorry.
Okay, thank you, Subhajit, for the wonderful talk. Are there any questions for Subhajit?
I have a question.
Sure.
Yeah, please.
Okay. So at the beginning of the talk, you mentioned this theorem which says that PC equal to PC slab for ZD, Euclidean lattices. So I was So I was wondering, perhaps you could, perhaps you can make some statement. I don't know, but perhaps you can make some statement for non-positively curved backgrounds. For example, I was thinking the following. For example, if you have a product of 2 trees, then at PC, there is this argument by Hutchcroft that the percolation, you cannot percolate along embedded Z2, right? Along
right.
embedded Z2, because that represents an end.
Yeah.
So slabs there, in products of trees, slabs are basically, if you can percolate in a slab, then you can percolate in that isometrically embedded copy of Z2 as well, because it's a tree, right?
Right.
And
yeah.
So can you say that for, if you have a product of hyperbolic groups, then, so this means that PC is less than PC slab, right? There's a strict inequality. So my uninformed is that there is a strict inequality for product of hyperbolic groups.
Okay, maybe Tom would be the better person to ask this question. So, you're okay. So, right. So your sense of slab is that okay? You take the beginning of this embedded C2. That's what you're saying, right?
Yeah. Because if you have non-positive curvature background, then you shouldn't be able to percolate inside. A slab and.
Yeah, that can happen. But you see that point. Yeah, I agree with that thing morally. But you see the point of all this thing is that if PC slab or whatever, let's call it something, this auxiliary threshold.
Yeah.
The main purpose of this, of designing that is, okay, so let me say something. Yeah, okay, I think that's important. Again, this will, okay, what you're saying is actually also morally correct, but you see, for example, for non-amenable graphs like that, okay, you essentially have a regime which is not strongly, you see, so for example, what you can do with this PC slab business, right? You can prove this local uniqueness properties and these things like that, right? And
yes.
But these graphs you have, you see, PC and PU are strictly different. So what you are saying is kind of also like a finite volume analogs of that, okay?
Yeah.
And that's very true. Yeah. So what here actually I'm concerned about more is that the cases where that is not the case, where actually PC and PU are same. Okay.
I see.
Okay, and there to obtain, my goal is to obtain a proper finite ball analog of that, and which I actually tried to convince you about that. PC slab is, well, it is a correct thing to do for Bernoulli percolation. For other percolation models, it's not. So
I see. Yeah.
I don't know if I could make sense to you, but
yeah, that makes sense. That makes sense. Yeah.
That's
okay. Thanks.
Okay. Are there any other questions? All right. So if there are no other questions, then let's thank Subhajit again.